Welcome. Now we're going to consider some operations on sets so that we can develop more fully the idea of a group. And afterwards we'll expand that into the idea of a ring in a field. So let's begin. It's possible to introduce two algebraic operations of the cardinalities of sets. And since we've already considered the union, we'll now consider the disjoint union of two sets A and B, which is the unions of these sets when they are viewed as being formally disjoint, such that any element in the intersection is then an element that can be viewed as A from the first set A, or A sub B, which is a set element of the set B. That is, if you have a set 1, 2, 3 and a set 2, the disjoint union of those two sets would be 1, 2, 2, 3, where the 2's are considered different because they come from different sets. Of course, if the two sets are actually disjoint, then the disjoint union of them is identical to the union of the two sets. Next, we'll define the Cartesian product of two sets, which is the set of elements which we considered as ordered pairs, x comma y, or x is taken from the first set and y is taken from the second set. Once we have these, we can define the sum and product of the cardinalities of two sets as the cardinality of A plus the cardinality of B is equals to the cardinality of the disjoint union of A and B, and the product of the cardinality of A and the cardinality of B is the cardinality of the Cartesian product of the sets A and B. As an example, if A is the set 1, 2, and B is the set 3, then there are two elements in this set, namely 1, 3, and 2, 3. We'll note that in kind of the standard way, the Cartesian product forms a matrix with number of rows and number of columns equal to the cardinalities of the two sets in the Cartesian product. It's fairly clear that these operations are well defined in the sense that if you have sets that are bijective to two sets, then forming disjoint unions of those bijective sets is the same as forming the disjoint union or product of the original sets up to a bijection, namely that A prime Cartesian product with B prime is equivalent to A Cartesian product B if A prime and B prime are equivalent to A and B, and likewise for the Cartesian product. In particular, since we've defined the natural numbers in terms of cardinalities, we can consider if these operations are defined on the natural numbers, and if the sets are finite, as well as if the number of sets is countable. If this is true, we have the following laws, which are easy to check, namely the associative law for addition, that A plus B plus C is equal to A plus B plus C. Commutative law, namely that A plus B is equal to B plus A. Associativity for, again, but this time for multiplication, A times B times C is the same as A times B times C. We have commutativity for multiplication, A times B is equal to B times A. And finally, we have distributive law, which uses both operations, namely A plus B times C, the same thing as A times C plus B times C. And we can verify these really quickly, letting little a be the cardinality of a set A, B being the cardinality of a set B, and C being the cardinality of a set C. Then we see that B plus C is the cardinality of B disjoint union with C. So if we consider the first half of our associative law, we have the cardinality of A disjoint union with the set B disjoint union C. And then that's clearly the cardinality of A disjoint union B disjoint union C. Likewise, we can do the same for the other side, considering A plus B as the cardinality of A disjoint union B, and then adding on the cardinality of C by disjoint unioning it. Likewise, we can do the cardinality, we can consider commutativity by noting that the cardinality of A disjoint union B is the same as the cardinality of B disjoint union A, since disjoint union doesn't care about the order in which we put the sets. Finally, for multiplication, we have B times C is the cardinality of the set B Cartesian product with C, and so A times B times C is the cardinality of A Cartesian product the set B Cartesian product C. And that's a little hard to visualize, so you can either consider that as a formal product of three elements, or you consider it as a matrix that extends in three dimensions, a bit like a cube or rectangular object in 3 space. These Cartesian products don't really care about if the first element is one element and the second element is a pair of elements, namely, as we have in this case, a comma the object b comma c, and we just call that a comma b comma c. It's bijective to that. And then we can do the same thing with a times b times c, which is the cardinality of a Cartesian product b Cartesian product with c. Finally, we have that a dot b is the cardinality of a Cartesian product b, and we note that Cartesian product doesn't care about the order in which we give it the sets. So we see that, namely, we don't care about the order because we have a very simple bijective mapping between x comma y in the Cartesian product of a comma b and the elements y comma x in the elements of b Cartesian product a. So we have a times b is equal to b times a. And finally, for the distributive property, we will note that the Cartesian product of some sets disjoint union against each other is the same thing as the disjoint union of the products of those sets. So we can expand that out, namely what we have here. We can expand that out and we get a times c plus b times c is well defined, and we get that it's equal to the other half of our equation, namely the Cartesian product of the disjoint union of Cartesian products. An interesting thing to note is that usually instead of writing a times b, we just use placement notation and say it's ab, and we drop parentheses whenever the associative laws kind of indicate in which order we should indicate which is the specific result that comes from applying the laws. So for instance, a plus b plus c, instead of writing a plus b plus c, because those are equivalent under associativity, so you have one specific answer. However, we should be very careful, in general, like in normal grade school math, that parentheses are sometimes necessary and that we use them when they are necessary, as is given by the case of a times b plus c, where there are two valid answers that can be unequal if you do not insert parentheses beforehand. Generally, it's safer to insert parentheses if you're in doubt. We can now continue to expand on the structure of natural numbers by considering the addition of natural numbers and its connection to disjoint unions. To take the successor of a natural number a, which is the cardinality of a set a, we have the successor, which is a prime, and we're going to call that the cardinality of a set a prime, where the set a prime is derived from a by adding another stroke to a, namely a disjoint union with slash. Therefore, the cardinality of a prime is equal to the cardinality of a plus the cardinality of 1 slash, so a prime is equal to a plus 1 for any natural number a. This provides another way of considering the successor operation on the natural numbers, and we have the standard algebraic machinery that we've all learned in high school or middle school. Next, we have the cancellation law for natural numbers, namely that a plus n is equal to b plus n for any three natural numbers if and only if a equals b. One direction is very easy. If a equals b, then clearly a plus n is equal to b plus n. However, we can establish the converse by inducting on n. This is because we'll start with the base case of 1, and we note that a plus 1 is equal to b plus 1 is equivalent to a prime is equal to b prime, but by our definition of the succession operation, this implies that a equals b. Therefore, if a plus n plus 1 is equal to b plus n plus 1 for some n in n, then a plus n, the successor of a plus n, is equal to the successor of b plus n. So by succession, a plus n is equal to b plus n. And then we can induce over all n, and we get a equals b. This is very important for extending algebraic operations on the natural numbers into a more complex structure. We'll note that there's no analog of the cancellation law for infinite cardinals, because we see that aleph null is equal to aleph null plus 1 is equal to aleph null plus 2. However, if the cancellation law did exist, then we could subtract aleph null from both sides, and we get 0 equals 1, which is a contradiction. Therefore, no such cancellation law exists. Finally, we'll consider an order relation on natural numbers, namely if a is less than b, where a is the cardinality of some set a and b is the cardinality of some set b. Then we know that there's an injective mapping F from A to B, but there's not a bijective mapping between them, as we defined before, considering partial orders on sets, on the natural numbers. So we can define that B, since there's no bijective mapping, we can say that B is a collection of strokes which is bijective to A as long as we append some additional strokes contained in the set C. So we get B is equal to A disjoint union of C for some C, and therefore there exists some C such that the cardinality of B is equal to the cardinality of A plus the cardinality of C. Or if we go to the natural numbers instead, we say that for any two natural numbers, then A is less than B if and only if B is equal to A plus C for some natural C. This expresses the order relation for the natural numbers in terms of this group of operations that we developed, namely the ideas of multiplication and addition. Note that there is not a similar characterization of the order relation A less than or equal to B, because there is no natural number that expresses the equivalence class of the empty set, which is something we'll extend to next time. Thank you.